Good morning, everyone. I like to welcome everyone for this two-day workshop on quantum computing and communication. This is the fourth workshop in the quantum outreach series that we have started from the 2nd of June. And this event is very special because we have esteemed scientists from Indian Institute of Science, Professor Arindam Ghosh. Thanks for accepting our invitation, sir. And we also have many participants joined over the YouTube live stream, so I welcome them as well. So I'll briefly introduce Professor Arindam Ghosh before he can deliver the talk. Professor Arindam Ghosh is a condensed matter physicist and a professor in the Department of Physics, Indian Institute of Science, Bangalore. He was awarded the Santi Swarup Bhatnagar Prize for Science and Technology, the highest science award in India for the year 2012. In 2020, he was awarded the Infosys Prize for Physical Science, the most prestigious award that recognizes achievements in science and research in India. His current research interests include the transport properties of two-dimensional electronic systems in semiconductors, carbon-based low-dimensional systems, optoelectronic properties of atomically thin semiconductor membranes, magnetic nanostructures, and structural stability of nanoscale systems, such as metallic nanowires and nanoparticles. Now, I would like to invite Professor Arindam Ghosh to deliver his talk. Thank you, sir. Sure.
Thank you. Is it okay if I turn this one to us? Okay, thank you. Thank you. Can I get started? Well, it's a pleasure to be here at C-DAC for the first time. We have been interacting with scientists from C-DAC in IISc for a few times because this quantum initiative, there's a very strong collaboration between C-DAC and IISc, and we are developing several things together. Particularly the superconducting, the Center of Excellence in IISc and the quantum is partnered with C-DAC and RRI, so we have to meet each other and have more closer interactions, and which is why the first opportunity I got, I thought I must come here. I am, as was introduced, I'm at IISc. I come from a little bit different background than quantum computation, but I'll show where my work is connecting to quantum. My lab is an experimental lab. In IISc, we have built about last 15 years or so. I have dilution refrigerators. I'm a low temperature physicist looking at electronic transport and optics, which is why the quantum effects are very important, because if you have to go to temperatures in the millikelvin region to get the quantum effect started. In addition to that, we have got a series of equipments and infrastructure to make electronic measurements using probe stations in presence of light, which is also a light matter interaction where optoelectronics and sensing with single photon detection, which are extremely important for quantum applications. That's what we do in my group in Bangalore, in IISc. We have our own scanning electron microscope. We have our own clean room for device processing. If you ask me, I'm more of a device person and device physics person. So we make interesting new devices and try to understand the properties of electrons and properties of light in such devices. I'll give you some examples in this talk today. So this is overall cross-section of the group. We do engineering, we engineer our materials. Two-dimensional structure is about 60 to 70% of our interest. However, we do work on semiconductors, which are directly implemented in quantum applications, quantum computing, quantum qubit formation, etc. I'll give you one example on that. We make our devices and we work at low temperature. So very quickly, what we do, we make our research interests are strongly connected to the interaction between light and matter. When light comes on a semiconductor, it produces electrons to give you current. So this is what we create, semiconductors of different types, so that the conversion of light or photons into electricity can be maximized. And that's necessary if you want to create a single photon detector, for example. So that's one example. In addition to that, there are other interesting areas which is not particularly connected to the workshop today. So I'm not going to talk too much about it. The neuromorphic devices are one direction which we are very excited by. Brain, the way you can devise or make systems which mimics the brain or brain activities is something which is taking a very interesting direction in global research today. One of the longer term goals of, I would say, quantum as well, would be connecting qubits, brain mimicking electronics coming together. So it's some form of a quantum neuromorphic devices in which we look at quantum circuits that can make its own decision will probably be coming there. It's not passive qubits anymore where you engineer the phases, etc., and like entanglement, but also smart qubits, maybe at some point of time in the near far future, will become important. So one of the directions of this, right now our work in neuromorphic devices are purely classical. There's no quantum in it, but we are keeping an eye open with how one can couple the quantum part and the neuromorphic designs to come together. So I'm going to give you a little bit of snapshot little later in the talk about this new hardware and the low noise optoelectronics and single photon detection using this. So this is where our contribution to quantum comes into play. Before I go to that, I would like to put these things in the context. I'm reasonably certain all of you here are aware of what's happening, what's the excitement in quantum in India, in particular with all the national mission coming up. I would like to put this in a little bit of a context where the importance of our work is. As you know, there are 4 different verticals that are being considered in quantum mission, in which computation and simulation, then quantum communication, which is the workshop about, and the sensing metrology, and then there's a 4th vertical, quantum materials and devices. The 4th one, of course, is where I directly come from, but then what we are doing, we're trying to reach out to the computation and communication using new kind of devices that can be manufactured and characterized. Just to give you a little bit of snapshot of what is the goal of the mission going to be, several of us were part of forming this vision over in the next 6-7 years or so. As far as the computation is concerned, you know that our national agenda would be to make a 50 qubit or more superconducting processor, 20 qubit semiconductor processors, then photonic cluster states to quantum photonic processors, etc. So there is a series of goals in the quantum computation aspect. In the communication is something extremely important today. We are looking at least 100-kilometer QKD fiber based. Then we have got a trusted nodes over 500-kilometer network. So those are the communication goals. We also have a very strong emphasis on the sensing and metrology. We would like to create atomic magnetometer with femto Tesla per root hertz sensitivity. Using diamond vacancies, we would like to go for picotesla per root hertz in the next few years. So there are significant, series of agenda, the mandate for our quantum mission. But these need to be supported. These need to be supported by back-end electronics. These need to be supported by new material research. These need to be supported by certain amount of infrastructure, so that we have the entire chain. It's not that half the material we get from abroad and other half is made there. It needs to be completed together. So for that, the quantum material and devices would like to create semiconductor processing facilities, which is connecting beautifully to the national semiconductor mission, which has been recently announced. Let me tell you where semiconductors is going to come into play, simply because my work in my group involves semiconductors of new types. So for example, semiconductors would directly come into the quantum process, in which silicon germanium based silicon processors. There are, of course, several new type of semiconductors, low bandgap semiconductors like indium arsenide, which are used to make topological qubits. But directly in the next few years, silicon germanium based quantum processors, and they will also feed into the quantum silicon single photon technology directly, because you need 3-5 semiconductors to come in for low band gap semiconductors, which will lead to single photon detection in the communication zone of 1550 or so. We have peripherals, we need back-end electrons, and that doesn't need to be 5 nanometer node. It can be 150 nanometer node. We need analog to digital converters, the DACs, ADCs, high frequency silicon devices to digitize our microwave signals. So we require that. We do not have any of these in India at this point of time. So the peripherals, direct application, and also that necessary infrastructure that is required for that, essentially high quality semiconductor growth, molecular epitaxy, heterogeneous integration, where you have on a single chip the silicon oxide, say for example, or silicon nitride waveguides, and the single photon detector, and the nonlinear crystals for generating the single photons. Then it will come together. And so this heterogeneous integration is going to become an extremely important component if we are creating new semiconductor infrastructure. So this is where the research has to come in together, and there are 3 verticals in which we have the hardware, we have the single crystals that's required, high quality materials that needs to be procured or developed, grown, and the computation. So if you require new material, for say for example, we require new material for nonlinear optics, because we need to create a spontaneous down conversion or high chi2, we require to design those materials. So there is a computation part as well that should not be neglected. And altogether, we need to have all these will require the computation, communication, as well as sensing on new material platform or semiconductors and single crystals. I'm not going to go into detail of this. So where we are right now, we from the semiconductors, we require new nano device packaging. We have developed dedicated foundry for quantum enabled devices. For example, even if you go for superconducting quantum devices, the qubits, the transmon qubits, we still need to, in order to have a 50 qubits or larger number of qubits, you need to have high bandwidth JPA, Josephson parametric amplification. Now that's not made in India. So we need to have dedicated foundries for quantum enabled devices. So this is just one example. There are several others. We have devices for quantum technology and application for smart sensing, as well as semiconductors, as I told you earlier. In terms of new material, what we require topological materials, which will essentially lead you to new types of qubits. Topological decoherence free qubits is one of the big emphasis today. For example, Majorana fermion based qubits, which are protected intrinsically from decoherence effects. So this kind of materials are called topological materials on which such qubits can be created. We have novel superconductors. Today is aluminum-based junction. And one of the national mandates is actually to lift it up to 77 Kelvin. So maybe tomorrow we will require new type of superconductors to have the qubits operate at much higher temperatures. So anyway, so these are the directions. I would like my last introductory slide would be where the computation come into play, and this is where a collaboration between CMET and C-DAC would be particularly important. Of course, C-DAC, we are collaborating already in the qubit, in the superconducting qubit directions, but overall, there should be a significantly strong emphasis on the calculations, on discovery of new materials to achieve some of the agendas that's there today. Just to give you a national scenario, we have several places in India now, Bombay or around Pune, IISc Bangalore, of course, JNCSR, there are several unit here, C-DAC here, then we have got ISER, Trivandrum. There are several places in the nodal places in the country where very high quality material is being developed, and it would be nice to get a strong network of computational scientists, experimentalists, device physicists, and crystal growers come together and look at specific problems in quantum technology that we can solve. Okay, roughly the timeline. This is something which is my vision of the direction that we are going to take over over the next few years. I think in terms of where the market going to get benefited by quantum products is not quantum computer. It's more towards peripherals and say single photon detectors and sources, which can lead to new types of optoelectronic devices for smart cities, etc. So those will come to market earlier than full-fledged useful quantum computation. Although even a small noisy intermediate scale quantum era, this NISQ era, would probably lead to some revenue generation by putting toy models in the cloud. So that's going to happen by about, a reasonable. It's already happening, but about by the time 1,000-qubit computer comes from IBM, that's going to happen in the next 2 or 3 years. Typically, we need our materials and devices infrastructure at the state of the art by about 26, 23, 25, 26-ish, so about 4 to 5 years. Recently, what we did, we made a review article in Advanced Materials on what kind of new materials that will be required to achieve some of these ambitious goals in quantum in the coming few years. There are some of these materials are semiconductors, two-dimensional materials, or two-dimensional materials can be semiconductors, can be metals, can be superconductors. So I put them a separate category altogether. We have topological materials, as I told you, which can serve both high quality single photon source and detectors, or they can actually host new types of qubits like Majorana qubits or topologically protected qubits. So there's a significant direction of research going on in topological materials and novel superconductors, particularly the hyperconductors. So this is something which looks like the material agenda over the next few years. But whenever you have new materials, you need to characterize them, and the most important component in new materials is noise. And that's what I'm going to talk about a little bit, why noise in these materials, particularly taking semiconductor and two-dimensional materials in the context of quantum computation. So to give you why noise is important. So if you have this is an example. So today you are making one of the most important components of transmon qubit. It is an aluminum oxide, aluminum lucifer junction. Now you have an aluminum oxide layer, which is a amorphous system. There are clusters of atoms. Okay? Now what happens if there is some form of I don't know whether, okay, if there is a defect state, or it can be a cluster of atoms in aluminum oxide, and that defect state can move from two positions. It pulls to the qubit, the position of the qubit in the Bloch sphere, variously. One of the possibilities, it could be dipolar interaction, it could be phonon emission. That means if there's a structural change in the aluminum oxide, then that can change the state of the qubit of the that you have created by sandwiching that between two aluminum. So if I just assume one of those systems, which is just going back and forth between two states, then essentially, if you record the state of the qubit, you will see that it's continuously move between two states, up and down, randomly. Okay, so this is called a two-level system. These two-level systems are terrible for superconductor operation. Okay? We need to do something about it. But the problem is this two-level system, if you get a large number of them, what happens is you get 1 over f. This is my major class today about 1 over f noise in quantum devices. So how does 1 over f noise comes? If you have a single fluctuator, which is essentially going between two states at a rate of tau, then you create a correlation function, and then you Fourier transform that correlation function to get what you call a power spectral density. Power spectral density is nothing but if there's a fluctuating quantity, what is the magnitude of fluctuations coming from a particular frequency range? That's called power spectral density. So if power spectral density is S, then in that case, for a single fluctuators, it will become a Lorentzian power spectral density, something like. So if there are a large number of fluctuators, each of them will give you a Lorentzian power spectral density, and when you add them up for a real system where large number of fluctuators, you essentially get 1 over. That's my primer for 1 over F noise, which comes from a single, fluctuating environment. Now, why is it interesting? Imagine a qubit operating in a not just aluminum oxide. It can be a semiconductor where a qubit is operating on a semiconductor quantum dot. What happens is, if there's a charge sitting somewhere nearby, and that charge is continuously going away and coming back, essentially is continuously providing a fluctuating Coulomb potential on the qubit object. And that leads to noises. Why I'm worried, I'm going to show you in a minute, because a charge causes decoherence. The charge makes the quantum information to decay with time. The low frequency noise is very common. If you take any electronic device, you know much better than me here, you have all the op amps or resistors usually come with a spreadsheet of that sort, in which you have 1 over F noise region at lower frequencies, and then you have got the large frequency region, which is usually dominated by Johnson noise and short noise for other applications. So typically in a quantum device, if I measure the charge, some electronic properties like voltage, current, resistance, inductance as a function of time, you will see these fluctuations. Typical magnitude of such fluctuations can be in the order of few picovolt to microvolt, depends upon how much current. Usually, if you're a quantum device, then you don't send current more than, say, a few microampere or a few hundred nanoampere, particularly if your device is working at a temperature of dilution refrigerator temperature, which is few millikelvins. You don't want to heat the device up by passing a lot of current. So you need to measure current, send current about few hundreds or nanoamperes. If that is the case, typically voltage fluctuations will go into the picovolt region to nanovolt. That's roughly the number that we're talking about. So these fluctuations then is what we can measure. In my laboratory, we have created infrastructure with which we can measure such low-level fluctuations at very low temperatures and look at quantum devices. So as I said, why am I worried about this noise when it comes to quantum computation? For example, if you take a look at the standard 8 qubit, which is given by the Hamiltonian on top, you have got that's essentially a pseudo, like a qubit is like a pseudo spin on rotating on the block sphere. And if your control field, like for example the microwave radiation that you apply to gate it or to change the state, etc., that's like a magnetic field which is coupling to the pseudo spin. Now the noise essentially comes as some form of a stochastic component on the microwave field. For example, the control field is B naught, and small b is like a stochastic field coming from the environment of the qubit that it is sitting in. And if that happens, then the evolution of the block vector will always accumulate a phase which is small phi, and then that you do a time correlation measurement, and what happens is e to the power of I phi, which essentially is the off-diagonal component of the magnetization vector of the qubit. It decays, as you can see, it's e to the power of minus time divided by t phi. The t phi is called the decoherence time, or what you call the inhomogeneous dephasing time in a qubit. Okay. What's the worrying bit is the inhomogeneous dephasing time, which is the time over which the quantum information decays, is directly proportional to the power spectral density of noise at zero frequency. This is a calculation which can be found very easily in the review paper published nearly 8 years ago. Now, if it is 1 over F noise, that means the power spectral density is divergent at zero frequency. The denominator is zero. Noise is really, really large, which means the dephasing time becomes very, very short. So we would like to have a system or materials or devices in which the 1 over F noise is minimal. If you want to make a qubit in that environment. So this is one of the major motivations in my group to find materials and devices to create to achieve extremely low noise, low 1 over F noise environment. Okay? So this is why we should be worried. And if I look at noise in quantum hardware today, there are several aspects. You have the electronic device performance. Obviously, signal to noise ratio goes down, but that limits the sensor, the SNR, the signal to noise ratio in the sensors and the detectors. But last point is a counterintuitive, extremely important point, that it also causes dephasing, not just degrading the performance. Okay, so I will give you two examples here. Well, I'll give you an example of what we did in the noise in a quantum computing hardware based on semiconductors. I'll show you some data on that, which happened in collaboration with with a group from University of New South Wales in Australia. And also I'll give you some little bit of description of noise that we do in photon counting devices. With our new two-dimensional materials, we make single photon detectors, and how we reduce the noise in those devices so that we are able to look at extremely high quality, single photons in measurements. Of course, noise is something which is, these are all based on 1/f noise. It's not all bad, or I am a fundamental physicist myself. So I not only try to reduce noise, but I also try to use noise in various aspects, but I'm not going to talk about that at all. We have been working on noise over the last 15 years, and we have looked at noise, how to detect novel materials and electronic properties in various systems. But that's a different story altogether. Okay, so coming to this old list, let me first say a little bit about the noise in doped semiconductors and how it affected, what kind of material we should develop, in which the noise will be very low. The reason of saying this is, tomorrow, if you are creating a material infrastructure in the country, what kind of direction we should take can give you, these kind of measurements can give you a direction. Okay. So this paper came out from the New South Wales group in 2 or 3 years ago, where you have seen they are unique devices. They take silicon and put an atom of phosphorus in that. Very close by, you can see the square over there. There are 2 small dots. They are individual phosphorus atoms, or maybe 1 or 2 atoms or something of that sort. They are separated by 30 nanometer. Now these are quantum dots. These are quantum, and the phosphorus essentially has spins, and those 2 spins interact with each other, and you can make the exchange interaction as a gate, and the state of the qubit is given by the spin. And you can see these gates out there. You can use these gates to change the exchange interaction, and you can show 2 qubit gate operations and so on. So one of the big goals of this group is to create a large number of qubits based on pure semiconductor environment. The reason is obvious, because we already have a $10 trillion semiconductor infrastructure in the world, so we don't want to go to another direction. They are strongly betting on semiconductor-based quantum processor. These qubits single T1 time, that is the energy within the single qubit energy relaxation, is nearly half a second, extremely long, and there's a reason behind it, and we figured out why is that so. Just to tell you a little bit about this very interesting material technique, because this might be interesting to people, even if you're not from the field. So they create these silicon doped qubits of using single phosphorus atoms in a very interesting manner. So they take silicon, and then they use a STM to selectively create holes in silicon. And because it's a STM, you can actually go and pluck atoms out by one, because the stability of STM allows you to access individual atoms. So you pluck one atom out, and then you put phosphine gas over there, and the phosphorus comes, and this red is circles are phosphorus. They go and get embedded inside silicon, and then you grow silicon again. So you now have individual phosphorus atoms precisely where you want them, like that picture out there. You can form arrays of single phosphorus atoms, dopants, creating a unique structure. Semiconductor doping is a very old system. I mean, people have been doing this since 1930. Okay? But now what these people can do, and now several other people in the world, you can dope phosphorus precisely what you want at 1 atom precision. So this is where the whole quantum regime becomes important. So this is very interesting direction. What we started doing on these systems, we started measuring noise. Now, interesting component here is this is not aluminum oxide, but this is doped silicon, doped phosphorus, which is entirely surrounded by crystalline silicon environment. So there is no oxide or no other bad charges that float around. And we found that fluctuations, very simply, you pass a current between two ends, these golden regions are the gold electrodes. I pass current here and measure the voltage. And the atoms are, the phosphorus atoms are down there embedded somewhere. The blue is silicon, it's in the big three-dimensional matrix. Phosphorus is red, which is essentially confined in a plane, wherever you want. And we found that the noise in these kind of materials is unbelievably low, extremely low noise. This is at 4 Kelvin because we couldn't simply measure the noise at dilution temperature. There was nothing. But at 4 Kelvin or so, this noise came up a little bit in the orders of a few nanovolt at a very large current. So when we compared it with all other systems, so there's a parameter called a Ghosh parameter, which essentially normalizes the noise magnitude that you get from different systems. You don't need to worry about the name itself, but look at the different types of two-dimensional systems used in electronics today. Look at the silicon itself, the MOSFET, silicon MOSFET that we have in our computers, and we have other kind of thermistors, etc. The noise in such kind of two-dimensional systems is extremely low, the lowest that we have in our technology today. Again, the reason we realized is because the phosphorus, the qubit, is essentially covered and circled in a completely crystalline environment. Not just two-dimensional system, then we started looking at, with a collaboration with them, one-dimensional systems. So now what they can do, as I said, they can put those phosphorus atoms however they want, wherever they want, because you are taking an STM and going and plucking atoms out. So completely under your control. So you can see these one-dimensional systems are also among the lowest noise that we know in low-dimensional structures like carbon nanotubes, like nanowires of metal, and various others. So you can see the last two are the noise magnitudes of the silicon phosphorus, doped phosphorus system, which at least the Ghosh parameter, which is again a normalized number of noise, is extremely low compared to other semiconductors and metal one-dimensional. Finally, we looked at a quantum dot, which is directly used in as a qubit, and there also it's like something like this. The way these quantum dots are made, as I said earlier, that you go and pluck atoms out in such a way that you create a quantum dot. The central region, the quantum dot of phosphorus atoms, then the source and the drain for the semiconductor is also made at the same time by plucking atoms out and forming larger structures. So those are essentially the one source and drain are indicated, and we can make a gate as well. So it's a quantum dot which is capacitively connected to the source, drain, and the gate. Okay. Now, if you create, this was a really interesting outcome of the work that we did. If you don't have any charge sources nearby, an entire system is embedded inside silicon, we see, we see a very interesting Coulomb blockade oscillations. You can see sharp peaks at as you change the gate voltage, and you see the well-defined quantum performance or single electron transistor performance for this one. However, if you plot, all you do is coat a layer of silicon oxide on the surface. Silicon oxide is amorphous. Silicon oxide gives you a large number of traps of charge, and you can see you completely destabilize the quantum device as you change the gate. They are not stable. They change with time, fluctuate randomly. So all these told us very clearly that if you are to make a high-quality qubit system, high-quality quantum processor with large or long decoherence times, we require to create a high-quality environment in terms of charge. So this is something which is also known even in the semiconductor, superconductor transform technology and other platforms for quantum computation. Well, but this was what our idea, our outcome was for all these measurements. Okay, so I'm going to take if you do feel have any, I'll be happy to answer because we will be moving from one system to the other. Okay. So this is the semiconductor that I wanted to talk about. Right. Oxygen always makes a difficulty because you start creating oxides. Although in case of aluminum oxide, it is necessary to form the tunnel barrier. But if something can be done, making the tunnel barrier single crystalline system without any cracks, then obviously that will improve significantly. So there are now architectures which are not scalable architectures. Aluminum oxide is a scalable architecture. You can make them very easily. The technology is now well developed. But you remove aluminum oxide, put a different type of tunnel barrier. That those things have been done, but I don't think they have been investigated in detail enough. But this semiconductor work certainly shows that oxygen is not. Yeah. I mean, presence of oxygen actually gives you lot of. Rather than oxygen, I would say oxygen. That actually is not good. Yeah. These are published papers now. So obviously, I mean, yeah, just let me know, then I can forward the papers. The website has the paper, but it doesn't have these figures. Okay, right. So now I'm going to go to the next one, the 2D materials. My group works primarily in 2D material business, and one of our goal is to look for quantum devices in which we can reduce the noise, because graphene and other two-dimensional materials are also very popular for various applications in quantum technologies. For example, well, I mean, the 2D material is 2D because you have a layered structure where the interaction between two layers is about 1,000 or 100 than a standard three-dimensional compound like ionic salt or covalently bonded CF4, etc. So this is why what you can do is that you can exfoliate these materials. I'll show you a little bit about the material designing technology that we have developed in the lab for the last several years. But in any case, I think we know about these kind of compounds. We have about 30, 40 of them. We have got graphene, which is essentially a single layer of graphite. We have the semiconductors. Graphene is not a semiconductor; it is a semi-metal. Whereas we have got the transition metal dichalcogenide, which are like molybdenum disulfide, etc., which are semiconductors, and they are amazing semiconductors. They have direct band gap, unlike silicon, which is indirect. But they also have extremely strong light matter interaction. If you take one molecular layer of molybdenum disulfide, you can take 5% of the light and convert into electricity. It is much larger than bulk systems like silicon or germanium. So that's why we were interested in this. In addition to that, there are high-energy superconductors, which are also layered materials. So in quantum technology, 2D materials are there everywhere. I mean, almost every aspect of quantum technology can get in principle affected or devices made out of 2D materials. For example, the electronics part, of course, is taken. That's the first. Through semiconductors like molybdenum disulfide, you can make transistors which are extremely low power terms. The reason why? Because if you take a silicon, you have, even if you go to 10 nanometer technology, as you go to 10 nanometer technology or 5 nanometer technology, then there is a very strong tunneling, or even in the off state, there is a very large amount of current. This is called drain-induced barrier lowering in electronic devices. Now that is inversely proportional to some power of the thickness of the channel that you have created. Now imagine a two-dimensional material like molybdenum disulfide, which is just about 0.3, 0.4 nanometer thick. All these miniaturization becomes significantly easier, and the drain-induced barrier lowering problems are much lower. So we actually can create electronic devices which are far lower in size and lower in energy consumption. In addition to that, there are novel superconductors, there are topological systems, the magnetic systems that down to atomic levels. We also have defects in these materials can work as beautiful emitters. for quantum communication. Emission, the defects of large number of 2D materials do emit primarily in the visible zone so far, if I know properly, but they are high quality emitters that you get out of your defects. People like me work on single photon counters by assembling these two-dimensional materials in appropriate manner. Then we have quantum sensing. The defects in boron nitride and others you can use as exactly the same way the vacancies in diamonds. So you actually can use these defects as a spin sensing, magnetic sensing, and applications of that sort. So there's a very large bandwidth of application. Just to give you an idea about how we make these kind of devices in the laboratory, we take a silicon oxide substrate, and we take a layer of graphene on a scotch tape. This is called a mechanical exfoliation. You scotch tape, you press the scotch tape on the substrate, and then you remove it, and you're left with a single layer of graphene on top. It's extremely easy, and which is why we could do it when without the infrastructure. But now, of course, the situation is much better. And then we put electronic using lithography. That's how a typical device would look like when you make it. This is simple. So when you measure the electronics of these kind of devices, you can see that silicon oxide acts, and that if I apply a positive voltage, the electrons are induced. If you apply a negative voltage, holes are induced. So the resistance comes down on both sides. So typically when we measure noise in these, we measure noise at specific points in resistance versus gate voltage curve. You can see that when the resistance is maximum, which is called at zero electron density, the noise is maximum as well. But if you induce holes or electrons in the graphene channel, then the noise decreases. Okay. So this is something which has been known for a long time. We have been working on this. What we did after that, we wanted to reduce these noise. And we found something really interesting. We found that if you take graphene and put it on a single crystal environment, this is what I was telling you a few minutes ago, instead of silicon oxide, which is an oxide, if I insert a layer of single crystal boron nitride, which is also two-dimensional materials, you essentially get a region. Now we measure the noise from both sides, from the part which is on single crystal boron nitride and the part which is sitting on oxide. You can see the noise from the oxide is 100 times larger than the part of the sample, the same sample, which is sitting on boron nitride, which is a single crystal. Again, the importance of high quality environment, charge environment is important. Now, I would give you a little bit of, I say that, okay, when I put the graphene on a boron nitride, there is a bit of material engineering associated. And this is called van der Waals engineering. And I'm going to tell you a little bit about what my group does in engineering new materials. And new materials means we can now take these two-dimensional materials layer by layer and stack them on each other in any way we want. So it's like, say, graphite is nothing but take a layer of carbon sheet and you put another on top, take a billion of them, and you make graphite from a single layer of graphene. Suppose I want something completely different, something completely new. And this is called what today van der Waals structures, in which I can take different two-dimensional materials and manually I can start stacking them on top of each other and make new materials. I can make any material that of any sequence that serves my purpose. For example, this, if I don't like this, I can take something, some other sequence and make it. So this is essentially creating solids with user-defined properties. I can take a molybdenum disulfide layer, I can take a graphene layer and put them together, and which is what we have done. And that turned out to be world's most photo detector. I'm going to show you in a minute. Okay, so how do we do this? This is a video for you, just in case it works. Let me see if it works. So we essentially do take one layer after the other, like this. So suppose I take a layer of graphene first. I want to make a stack of several 2D layers. Then I take a layer of boron nitride, and then I take a layer of another graphite if I wish to, and then I take a layer of chalcogenides or something of that sort, and I create a full layer. So this is something which is now a major direction. And okay, this, by the way, I'm showing this example to show how we engineer materials in my group. But this turns out to be the single photon detector as well. I'm showing how. So this is essentially a graphene which is on top, and then a chalcogenide layer at the bottom, essentially absorbing light, and that light creates electron hole pairs and sends it to the graphene layer in between, and we can count individual photon number in a bunch. The number resolving photon detector can be made. So this is something which is a real device. It's not just a cartoon. Okay, now coming back to the question of noise, we found that if I, instead of putting this on silicon oxide, if I take graphene and put that in between two layers of boron nitride, it's a beautiful single crystal environment. Noise comes down by a significant number. Then we have made some really interesting devices. I'm not going into the detail. What we understand in nanoscale quantum devices, how to reduce noise, we need to make sure that the substrate needs to be perfectly single crystalline. We need to have large mobility of the channel. We have to engineer the band structure a little bit. The electrical contacts are extremely important to decide what kind of contacting to use. All these are work that we have done to understand the origin of noise in these systems. We want to have single crystal channels. If you have polycrystalline, there's a lot of noise comes from there. Okay? And the metallic interface. So all these are our understanding over the last few years. So where we are, I'll give you a timeline here. So for example, when we started this work in graphene in 2006, 2007, the graphene noise was somewhere here. Oops, the graphene noise was somewhere around 10 power of -1, which is of the parameter called the Hooch parameter. There are other materials. Silicon MOSFET is also a very low noise system. So you can see the color code here. It's about 10 power of -4, -5. Today, by doing all sorts of chemical engineering of devices, we are somewhere here with the single layer graphene in 2020. We are almost ready to be implemented in quantum dots for quantum applications. So this is the amount of effort that takes to reduce the noise in such an environment of choosing the right environment for devices. Now I'm going to go to the second part, which is about 10 minutes. I think, what time do I stop? I have got, we can discuss whatever. Okay. Right. So is there anything at all? Otherwise, I'm going to go to the single photon counting, how we did that. Oh, okay, yeah, okay. So I can tell you the device that was used is this. So we had the lowest noise that we achieved in 2D, and it's a record today in the world, is obtained by putting a layer of graphene between two layers of boron nitride and a layer of molybdenum disulfide, screening all the charges. See, we found silicon oxide is a bad source of charge, right? But it turns out that even if you put boron nitride, which is expected to be a single crystal, has got large levels of charge because of the defects in the boron nitride. And those charges actually give noise. So whatever noise left is given by them. So we tried to screen that out by using another semiconductor, which screens the charges in the dielectric environment. And that led to an extremely clean two-dimensional system, which very low. Graphene, that's the lowest noise that people have observed. So that's the direction which we have taken in 2D materials. What I'm going to say now is, okay, how can we make such 2D devices into a single photon detector or high quality? First, our goal was not to make single photon detector. Our goal is to see if we can make a high quality photon detector. And let me tell you an idea behind it. Let's take a standard single photon detector that you get in the market, APD, or single photon detector, avalanche photon detector, or silicon-based systems. So you have, this is the generic. You have a P-type, an absorber region, and an N-type. Sorry, the amplifier is there in the between the insulator between the N and P region. It's like a diode, right? And when I apply the bias, when light comes, produces the charge, electrons and hole move in the opposite direction. And what happens is that they go through the amplifier region where there's a impact ionization that takes place, because an electron goes, then it hits an ion in the amplifier region, produces more electrons and amplification. That's what is called an optical gain. And that's how you create high quality photon detector, that a single photon can create a large number of electrons, right? So that's called that's an avalanche photodiode that is used in single photon counting, large number of quantum applications, in particular quantum communication. Okay. Now, if you look at the noise, where does noise come from? It comes because the amplifier region where the gain is happening, there is a stochastic recombination of electron and holes in that. So not all the electrons that started will eventually get. There would be sometimes there would be some holes will gobble up some of the electrons. So there would be a noise at the output in the current. Okay. So if you look at the total signal to noise ratio for an avalanche photodiode, it's given by that expression, which is essentially given by two sources of noise. One is the gain noise, and the other is the noise in the electrons. Right? So gain noise comes why? And this is actually turning out to be the most important source of noise in such kind of PPDs. That gain noise is because of the stochastic recombination, because the flow of electrons is coinciding where the generation of electrons happens. Right? Because you have the circuit, the light comes, it produces electrons, and the electrons actually flow in the same circuit. So there is the electrons are generated in the same path where the electrons are flowing, and that is why they are stochastically recombining with the hole somewhere and leading to the noise. So as it turns out that ideally you would like to make single photon detectors better and better by increasing the gain, but it doesn't work very well, because as you increase the gain, you see the noise increasing as well. So there's no point in increasing the gain too much. So that's the limit. That's the limitation that the silicon-based detection with APDs actually works. So what we wanted to do, we wanted to solve this problem. We wanted to solve this problem in a completely different way. So I'll tell you what the idea was. So the idea was, okay, let us do one thing. Let us separate out the generation region and the current flow region physically. The main thing is APDs is they're in the same range. But now suppose I do this van der Waals heterostructuring that I can do. By the way, these are now available even at the wafer scale. It's no longer a scientist taking scotch tapes and playing around. Now these are available in full wafer scale from different companies. You can actually create these large number now in manufacturing. Some people are doing it. So you have molybdenum disulfide, which is a semiconductor, and I put a layer of graphene on top by using the technique that I showed you earlier. Now what happens here, that when I shine light, then the light comes and hits the semiconductor. It creates an electron and hole, but the electron now comes out of the semiconductor and goes into graphene and gets physically separated, because I'm measuring the resistance of the graphene. So the current flows in graphene, but the generation of charge happens in semiconductor. That was the neat idea that we started doing this, and as I said, it is nothing but using the same kind of generation of. So this essentially you take a graphene layer up, then you take it, put that on a molybdenum disulfide, and then you put electrical contacts to measure the. That's the basic idea. So if I look at, so if I basic science of it, the electron and hole pairs are generated when light falls on molybdenum disulfide, and then the charge jumps out, the electron jumps out, goes into the graphene layer, and gives you the current, but the hole stays back in the molybdenum disulfide and doesn't recombine ever. So as a result, this simple idea led to 10 billion times enhancement in the sensitivity to light. So for example, this is measured by what you call responsivity, is one of the important parameters in finding out what is the efficiency of a photodetector in terms of how much current you get given the how much of power of photons that you fire at them. That type of typical silicon-based photodetectors have a responsivity of 10 power 1, is about 1 ampere per watt, current ampere in watt in power. Whereas these kind of detectors now can detect power efficiency 10 power 10 ampere per watt, which is, as I said, about 10 to the 10 orders of magnitude an ampere. So it was essentially a completely different type of detection. Now we have been able to make such detectors to measure single photons very nicely. For example, this is just from LEDs. We measure very few LEDs, very low current LEDs in which you can get very small number of photons in a bunch, and you can see that you can actually, this x-axis is the number of photons in every bunch of light that comes in, and we can see that we can see the individual photons that comes and hits the samples, because our current is proportional to the number of photons that come and hit the sample. We can actually look at the number of photons in a pulse of light, which follows the Poissonian distribution that I showed. And what is interesting about this is you can see that as you increase the intensity of light, the modal value of number of photons slowly shifts to the higher and higher. So this is a single photon detection, single shot current measurement, which is different from the standard single photon detectors in silicon or superconducting nano. Oh, okay, I'll tell you why I'm so excited in my last slide. But before that, I can tell you that we have now been able to do this even in the infrared region. So this is a very recent work. We have been able to manipulate this charge transfer, because these kind of detectors work very. The basic idea is essentially transfer of charge from the semiconductor layer to the graphene layer, and now we have been able to manipulate that charge back and forth, and we can make these detectors work beautifully at the same kind of or nearly same type of efficiency at 1550 nanometer communication. So we are talking about something which probably implementable even at a realistic scale. Why am I excited by this development? First of all, speed. We are talking about, if you take single superconducting nanowires, the advantage of people use superconducting nanowires because you can go to thermalization times of the jitter and the other kind of parameters. Superconducting detectors are in the order of around that. Here we are talking about a system in which the light is going from one layer to the other. That's the main speed limiting time, and that happens at frequency. So we are talking about a time scale at least a factor of 1,000 lower than that standard single photon detector. Because the electron has to transfer is just to go half a nanometer distance in order to be activated by light. So that's one of the huge, and this has been observed. Picosecond charge transfer processes are now established in such. That's number one. Number two, the operation temperature. We don't need superconductors. We are working at these, in these systems, we are working at 200. There are temperature operation. There it is. Our work has been to show these things and operation. We of course have to work a lot on the electronic component part of it, the back-end electronics. We need to do high frequency measurements. Those are the things that needs to happen now. But in principle, these detectors work at room temperature. It works at a, or it, in principle, shown by other groups, that the charge transfer happens at a much faster rate than you can think of in standard detectors. Okay. Of course, there are challenges, and I'm going to come to that. The challenges are efficiency, because we are talking about a single layer, maybe 2 or 3 layers of semiconductor, which makes efficiency 30% or so, which is again not too bad in many for many companies. If you take a standard silicon, then we are talking about doing communication at 20%. Many of your detectors are 20%. So we can increase that. We will be able to, just by using a larger, thicker semiconductor, we will be able to increase efficiency by absorption. Okay. We can now integrate electronic chips. There are papers which are doing now, and we are doing that in the ISC as well. We take this to the, as I said, one of the major directions will be in heterogeneous integration, where a photonic circuit and two-dimensional materials will have to come into it. And now that what we can do, or before this one. Okay, so this particular data was done at 80 Kelvin. So this is still above the liquid temperature. But it works, this detection at 1450, if I know it works up to about 200 to 120. I remember whether we have done this at room temperature. That's right. So that's our goal is that to go to photon detection in this frequency. But with a completely different architecture. We don't want to use silicon for this. Of course, I have to check in the lab. I think we already are at room temperature, but we need to see. We have so far certainly showed the room temperature performance at visible range. This is the room temperature performance of the visible range. But for the 1450 nanometer, I think we have got about 200. I have to check in the lab what's the maximum temperature. So the noise parameter, you mean to say, right. So, okay. Typically, I don't have the TP, the noise equivalent power, for example, is in the order of 10. Actually, I have it in the last slide. I'll show you. I have it in that list is there. Okay, so we are trying to now put this on a chip, and collect light which is coming to wavelet. That's ongoing work. Now this is the noise and the full structure. So you have the photomultiplier tube. We have got the silicon spads, the transition edge, and SNSPD. I'm just comparing where we are in terms of this and what the positive and negative. Everything is positive and negative. And our advantage is that we are working at a 100 to 200 Kelvin temperature range. Is the lowest line. I don't think you can see it from there. But anyway, we have right now okay. So this is an older slide. So we have extended the wavelength zone from 470 nanometers to 1500 nanometer. Efficiency is right now about 5% or so. We are increasing that to about 30% by increasing the layer of thickness of the semiconductor absorber. The noise equivalent power is in the order of 10 power minus 18. In comparison, if you look at the photomultiplier tube, it's more or less in the same order as the photomultiplier tube. The silicon pads are 10 power minus 13. The InGas is about 10 power minus 17. The transition, the superconducting ones are obviously low temperature. They will be low noise. So they are about the same order as power minus 18. The CES in 10 power minus 18 as well as SNSPDs are 10 power minus 18 minus 21. We have large number of gain. One of the very interesting aspects is the what do you call the linear dynamic range in our devices. The dynamic range can be extremely high. I'm not totally sure where we are going with it, but I'm sure we can measure about in nearly 60 decibels can be our dynamic range, which is something which I'm really looking into very carefully before I make very strong claims. But because at the end of the day, the amount of current we generate is proportional to the number of photons. Every photon is leading to an electron, and the larger the current. So we are actually initial results show it could be 60 decibels. 1,000, we can measure up to 1,000 electrons, for example, in single shot measurements. If that happens, and if you go to the noise level where you can make a difference out between 999 and 1,000, I think that would be a game-changing situation, particularly for quantum application in photonic application. For example, those which look at Gaussian boson sampling, in which you require a number resolving photon detectors. I think this might be an interesting solution. Okay. So that's all I say about my technical part. I mean, if there's any question, I have about 2 or 3 slides which I'd like to talk about what is happening in IISc in terms of quantum. One of is the member IISc's Quantum Technology Initiative. I would like to say a little bit about what is happening there, particularly because our interaction with C-DAC needs to become stronger, not just in one aspect. It has to come to photonics, communication aspect as well. So I thought I'll include a few slides at the end of my presentation today, so that we can find out where we can engage in more strong and meaningful manner. But if you have any questions in the technical aspect, you can ask. Because one of the help we will be requiring, my group, is creating an electronic support to this that we need. And we are working with some people, my group essentially, of course, of PhD students and postdocs who are working on various material designing aspects. As you see clearly that there are a large number of questions. What is really the noise? How much is the noise? How much is the dynamic range for these detectors? So there are many fundamental questions that we would like to answer. Yeah. Beautiful. So that will really be something that I would very strongly welcome, and we would be, very enthusiastic in taking this forward. Right. So this is precisely what the goal is. Okay. So let me tell you what is happening in IISc in quantum, particularly since 2020 September, when we created an initiative called IISc Quantum Technology Initiative, which has about 40 odd faculty members from 11 different departments. We realized that if you want to make a tangible impact in quantum technology domain, which is moving really fast all over the world, we cannot do it in an isolation. We have to come together, and because quantum technology is inherently a multidisciplinary initiative, we need to, and IISc already has that structure. It has engineering, 40 departments, it has got science of all types. We not only have people who can make things, but also people who can consume those. For example, you have a huge number of biological departments. And if you are making a quantum sensing for handheld NMR with a diamond-based sensor, we can make them and we can test them on various biological species and so on. So we have a full structure, so we wanted to make use of it. We came together and we started working on this. Of course, this already was in the COE, the Center of Excellence in Quantum, that already started with MIT funding and partnership with you. So our goal has been to sort of, there are people from physics, high energy physics. Apurva Patel is the convener of this initiative now, who is from Center of High Energy Physics. There are nanoscience and engineering, where all the fabrications are done. Department of Electronics and Systems Engineering. We have electrical communication engineering, where Varun Raghunathan is working on the communication part. Computational and data sciences. There's a lot of quantum algorithm part that's going on in CDS, as well as in computer science and automation. We have mechanical engineering department, applied physics. We have got materials research center, solid state and structural chemistry. So there are about 11 different departments which are right now involved, and there are more departments and more people, because we are looking at people with complementary expertise. So they can come from Center for Sustainable Technologies. There are different departments. We started the first MTech program in the country dedicated to the quantum technologies. We are essentially training people up from algorithm to the communication hardware, computation hardware. So there's a whole round expertise quantum that is being developed to students. It has started with low key. Now we have slowly number. It's a once quantum becomes a norm, I'm guessing this will become a significantly well endowed program. But it's increasing every time. As I said, we are looking at hardware, very strongly dedicated to build quantum hardware in the country. And our clean rooms and all the fabrication and processing we have are being used to the full for this clean rooms and SEMT and to give you a snapshot of what we have been doing, our quantum activities over the last 2 years or 3 years. As I said, first is quantum hardware, in which we are developing a multi-qubit processor, and C-DAC knows about it because we are partners on this, which Prof is making in 4-qubit, and we would like to now go to the next phase. The photonic processor on a chip is now a new initiative in which we would like to create a fusion-based quantum processor, in which 5 to 6 resource states, each with about 3-4 entangled qubits, photons, something that we are trying to build. Peripherals and support electronics, the cryo-electronics in particular is being developed at the Department of Systems Engineering. In addition to that, we have got communication aspect. We have now quantum sensing and magnetometry, particularly the support from DRDO. We are trying to develop the high sensitive magnetometers using quantum nitrogen vacancies and various types of other methods. And of course, my group and several others are now involved in making photon sources and photon detectors and trying to couple them on each other. So this is what is happening in the single photon counting and source hardware. Now, these 3 directions are funded. Not only funded, the Center for Institute itself gets some money, as well as the COE. In addition to that, we have our strong software-based initiatives. We have ML. We are talking continuously with our computer science and automation and data sciences departments. We look at algorithms, the error-resilient algorithms. We are looking at simulations, and we are trying to develop quantum-inspired classical algorithms. There are algorithms which can, for classical systems, can work very well if you take quantum components into that. And of course, there's a huge work that is going on in the post-quantum cryptography. What's happening now? So in addition to that, we have started a new direction, which is called a quantum research park. And this has now been funded by Karnataka government, which is extremely new and I would say visionary step by the government here, that they would like to create a similar kind of supremacy in information technology in quantum computing as well. So the goal of this quantum research park, and the funding has been approved, is on its way, is to create a multiple or a multilateral interaction between industry, government laboratories, IIC, and colleges and universities in Karnataka. So we are trying to create a shared infrastructure which people from industry and colleges and universities can access in order to do their quantum work or quantum experiments, train them, get domain knowledge in this area. And we are trying to create an industry IISc consortium, industry IISc consortium to mentor startups which are coming up in this. There are about 4 or 5 already in Bangalore itself, which are either looking at quantum communication, quantum computation, detectors. There are startups in all 3 different directions. And we would like to see how a centralized resource, which is experimental resource, can help them grow as well as give them mentorship. So that's essentially into entrepreneurship and outreach that's coming up at IISc. In addition to that, we are talking about human resource generation. This is something which I would believe the biggest problem in India in any field, not just in quantum, and quantum particularly because it's a new field. The dedicated MTech program I talked to you about, but we are also having a series of PhD students and postdocs now in this direction. We are also trying to improve this by starting new fellowship schemes. We have our global partnerships now with all sorts of different overseas institutions, as well as using chairs professorship and visiting professorships. And all our activities are in alignment with the national schemes, the national missions, which are either NMQTA or Quest or COE. So we would like to move in this direction. Give you a little bit about the last couple of slides, what kind of vision that IISc has in the next 5 years or so in terms of quantum. So we are trying to now develop, as I said, industry consortium to access the joint facilities. I give you a description of that. The goal will be to write joint proposals and find money for that. We are trying to develop certain focused quantum laboratories. Give you an example here. Kind of laboratories we have in mind in the next 5 years. In IISc, we have or we would like to build expertise in those areas. We are reaching out to various directions. We would like to create in IISc premises now a hardware of 50+ qubits. We have now the know-how in the two-sphere mighty COE. We have now got the basic structure going. We have multi-qubit processor. It's time to scale it up. It's time to scale it up to a number which is respectable at the global scale. IBM will probably cross 1,000 in 2024. As a country of 1.5 billion, we don't have more than 4 qubits. That's not right. So we would like to have something within, and make it available in the cloud or whatever. And we have the basic necessity and basic structure to do so. And we would like to create the infrastructure around it also in Bangalore or in For example, we would like to make our own Josephson parameters of large bandwidth. Can we do that? For that, we need to have a tool. We need to have a structure which is dedicated towards it. It's not a shared structure. Center for Nanoscience today has excellent structure, excellent price process and characterization. But they're shared. But they're shared with people who are doing semiconductors, people who are doing materials, people who are doing something else. We would like to have a dedicated. So this is something which we are looking out of. We are making our own quantum process, photonic processor direction is another lab that we would like to dedicate, in which we would like to create a 20-mode quantum photonic circuit in the next 2 or 3 years. That's roughly our time scale. As I said, there's about 5 to 6 resource states with fusion computation, and we would like to see the difference that we would like to make, and where we will be different in the world is we would like to make with our detectors or new detectors or different ones. I'm not the only one working on detectors. There are other faculty members who are working on single photon detectors, working at room temperature. So we would like to see if these kind of activities can be pulled to room temperature entirely. And this is what our bigger goal, bigger vision is, because even if you go to the quantum photonic processors from Canada, from other places, like quantum, they are all, okay, the initial core element is at room temperature, but the detector is single superconducting. They are not low temperature. We would like to solve that problem and see if we can do it for the first. So we have then semiconductor-based processor. This is something we do not have, but it's again in alignment with national agenda. But we have people who can start this. We are looking for faculty members as well who will be dedicated. Similarly, we do not have trapped ion source. So we would like to look at that new trapped ion and neutral. We unfortunately lost faculty members in that direction, but we would like to look at, not because just quantum computation, but trapped ion and neutral ion laboratory would also look at sensing, magnetometry. So there are advantages why we would like to invest significantly in this direction. And communication. In terms of communication, we have a plan in the next phase, in next 2 or 3 years, to create a network within the campus, but with a scalability aspect, and see if we can do it in that system. And this is probably where a strong engagement with C-DAC is extremely important, and we should start the dialogue now rather than leave it for later, and see what kind of logistics that we need to start. I know there are dialogues with IIT Madras and C-DAC, but we would like to go with a certain unique aspects with our network, the kind of devices that we would like to use, the kind of communication with fiber optic. It should be probably will be with fiber optic with the trusted. What kind of logistics that we need to start talking about. So, but in the next few years, already the goal will be to create a campus-wide network. But let's see if we can include Bangalore itself. Okay. And finally, we would like to have a quantum sensing laboratory in which we would be developing sensors, not just for for laboratory purposes, but we have as I said in the beginning, we have a whole biological system around it, and there's a new medical school coming up in ISC. So we would like to direct or focus our sensing activities towards biological detection, medical diagnostics, and so on and so forth in a specific manner. Also use it for other kind of material characterization, strain sensing, temperature sensing, and so on and so forth. So these are overall directions in which we would like to go. My last slide is this. Okay. So of course, there are other things here, but if you are to believe this NASSCOM, I don't know, the NASSCOM outlet from February this year, that a projection in the future, this is just on the quantum computation, that somewhere around the inflection point of 2026, 27, the value addition to the Indian economy can go to a very large number. Now, we being scientists, we need to be realistic here and see where it really goes. But it could be a possibility if we can dedicate and if we can focus our activity in the broad spectrum of quantum technologies, and this is not going to be a very difficult target. Thank you. That's all I wanted to say. We have single photon detectors, but it is at the laboratory scale. So it's difficult to shift it because you have to shift the electronics as well. But yes, we do have single photon. The single photon detection itself so far has been tested at temperatures of about 100 to 150 degrees. We are increasing the temperature now. Kelvin, yeah. No, I don't make processor. There are my colleagues in ISC who are involved in making multi-qubit superconducting processor. At this point of time, I think the goal is to make 4 or 8 qubit processor in the next 1 year. But we are now looking at the possibility of increasing this to right. So we had recently a ISC industry consortium in which about 15 industries came over, and there is a huge interest both from local startups as well as multinational MNCs. Now, what is happening here is most of the people are looking at training because we have algorithms being developed. We have soft part of the, say, for example, what kind of software that will be required to do financial transactions, to medical diagnosis, drug discovery, using a quantum computer. There's a huge interest in that direction. In terms of developing the hardware, which is what we must need to invest now, if you want to take leverage of all the soft development that is happening. For that, there are about 3, 4, 5 companies which are starting, and I'm hoping that they will grow in that time. So there is a lot of interest from both MNCs as well as local staff. And I'm reasonably certain that good. Good. Yeah, I mean, of course, you cannot leave out atomic clock. Yes, answer to your question is yes. There are now my colleagues in ISC who are working on atomic clocks. We are looking at this is being done in collaboration with DRDO. In Center for Nanoscience, we are looking at frequency abilities in the order of 15 minus 15 areas. So something which definitely one can do. Yes, that's that is these are on our agenda. The work is already starting. Biological detection will be one of the most important applications. Specific cancer detection or is probably little premature at this stage. However, there are now microscopy which work on entangled light sources, which show that you can go below the usual noise limit in microscopy. And if there are, and there is a lot of work happening in NMR, particularly using not just nitrogen vacancies, but hyperpolarized carbon. So various NMR detection schemes are coming up. I'm guessing the cancer detection will also be one of the beneficiaries for all these developments. And if you ask me, I think as far as quantum technology is concerned, this is the part which will come to the market first. And in a full-fledged product, useful product. And that should be happening in the next 4 to 5 years.